Today let's look at spinny stuff. Whether it's a satellite orbiting the Earth, you going round on a roller coaster loop, or me just spinning on my chair, circular motion's everywhere. And if studying circular motion makes you dizzy, then this video is just for you. Did I really just say that? Let's start with the basics. Let's look at a circle. One complete loop of a circle has a path length of 2 pi r. Let's give the path length the symbol s, and we can show that for a complete circle, s over r equals 2 pi. If we had half a circular path, s over r would be equal to pi. In fact, for any arc around the circle, then s over r can be represented as a fraction of 2 pi. We call this value the angular displacement. I find this ratio very pleasing, and there's a certain beauty to pi that should be admired even by non-mathematicians. Anyway, enough fluff. What's the point I'm trying to make? Angular displacement has a ratio s over r, and it is a ratio, there's no units. The numbers spewed out though we do term as radians, just to differ it from degrees. This is where 2 pi radians is one complete circle, or 360 degrees. Angular velocity gives us the rate at which the angular displacement is changing. So angular velocity is just angular displacement over time. And we give angular velocity the symbol omega. So omega equals theta over t. How does angular velocity relate to linear velocity? If we take the arc of a circle, AB, and rearrange our equation for angular velocity so that theta equals omega t, then we can see that s over r equals theta, which equals omega t. Rearranging this, we get s over t equals omega r, and since s over t is just linear velocity, we get v is omega r. This gives us the tangential velocity of an object travelling in circular motion. If I swing a ball on a piece of string around my head and then I let it go, it will travel off with this tangential velocity, according to Newton's first law.
Carl?
As an object travels in a circular path, its velocity is changing, although its speed may be constant. This is because velocity is a vector and it's changing direction. Now, if its velocity is changing, that means it must be accelerating. This acceleration is directed towards the centre of the circle. Now, interestingly, although it's accelerating towards the centre of the circle, it's not getting any closer to the centre of the circle. The magnitude of the acceleration is given by the equation A equals omega squared r, or A equals v squared over r. If there's an acceleration towards the centre of the circle, then there must be a force acting to cause that acceleration. That force is called the centripetal force, and that acts towards the centre of the circle. As I'm sure you know, the resultant force F equals ma, and so we get the equations F equals m omega squared r, or F equals m v squared over r for centripetal force. There are lots of examples of centripetal forces, one of the most obvious being gravity, which holds two objects in orbit, like the Moon and the Earth. Now let's settle something serious. Centrifugal force, is it real or not? In the context and frame of reference that we've been discussing, no. And that's that. A centrifugal force is best thought of as what people experience and feel when a centripetal force actually acts. If you're in a car that suddenly turns one way and you're thrown against the side of the car the other way, then what you're experiencing is not really a centrifugal force, it's your mass's inertia trying to keep you going straight on in a straight line while the car is actually veering off to the side. People often call centrifugal force a fictitious force. It's not going to come up in your exams, so get it out of your head. In a moment I'm going to go through some examples, but I need to remind you that there's some questions and some worked answers available for you to download for free from my website that go nicely with this video. There's a link in the description below. To continue to produce these videos and resources for free, I do need to ask you for your support, so if you could like and subscribe, that would be really helpful. I also read all the comments, so if you want to ask a question, please do so. Now let's look at an example. A small object of mass 0.3 kilograms is attached to a string and is swung in a circular path at an angular velocity omega of 6 radians per second. The string length r is 0.5 meters. 1. Determine the tension in the string required to keep the object in circular motion. 2. If the tension in the string is increased to twice the required tension, find the new angular velocity and tangential speed of the object. So tackling one first, the centripetal force acting on the ball is due to the tension in the string. And so the tension is the same as the centripetal force, which equals m omega squared r. Putting our numbers in, we get 0.3 times 6 squared times 0.5, which equals 5.4 newtons. Part 2, if we double the tension, then 2t equals m omega squared r. So 5.4 times 2 equals 0.3 times omega squared times 0.5. Rearranging that, we get the root of 10.8 over 0.3 times 0.5, which equals omega, and that equals 8.49, more or less 8.5 radians per second. The speed is found from v equals omega r, which equals 8.49 times 0.5, which equals 4.2 meters per second. So there we have it, a quick look at circular motion, which I hope you found useful. If you have, please do look at this.